Hi, I'm Matthew Kay, and I'm going to talk to you about ggdist, Visualizations of Distributions and Uncertainty in the Grammar of Graphics. ggdist is both an R package and a formal way of describing uncertainty visualization using distributions. There's a wide variety of interesting uncertainty visualization types in the literature. However, existing Grammar of Graphics implementations remain relatively limited, sticking mostly to intervals, densities, and uncertainty bands. How would we describe this richer universe of uncertainty visualizations? ggdist provides a small number of geometries and statistics that can create a large variety of uncertainty visualization types. It does this by formalizing uncertainty visualization as a form of distributional visualization. Let's see what that looks like. Here's a simple point interval chart that contains a point, a 66% interval, which may be a Bayesian credible interval or a frequentist confidence interval, and a 95% interval. ggdist provides distributional aesthetics in addition to the traditional Grammar of Graphics aesthetics like position or size or color, onto which probability distributions or confidence distributions in the frequentist mode may be mapped. Here, a normal distribution parameterized by mu and sigma is mapped onto the X distributional aesthetic. Given that mapping, we can then describe the endpoints of a 95% uncertainty interval using the quantiles of the normal distribution. This is a little bit unsatisfying though, in that we'd like to be able to generalize this to describing the endpoints of intervals of any mass. So if we think of the mass as gamma, say, in this case, being 95%, then the endpoints of the interval are 1 plus or minus gamma divided by 2. Now that gamma is data, if we actually consider gamma to take multiple values, say 95% or 66%, and we think of mapping gamma onto the line width visual aesthetic so that, say, smaller values of gamma go on to thicker values of the line width, now we're able to describe both of the intervals in this visualization in terms of their mass and the visual aesthetic that the mass is being mapped onto. If we then instead say map mass onto color, and maybe even change the set of masses that we want to visualize, now we have an interval chart using color instead of thickness to display 3 intervals instead of 2. This generalization will allow us to describe a wide range of uncertainty visualizations based on interval representations, including, say, line ribbons and uncertainty bands, or even fan charts with gradients. If we wanted to describe something like, say, this density plot, where I've also left on a point and a 50% interval for reference, how would we do that? Well, one way of doing that might be to introduce a positional subscale, which ggdist calls thickness. We use a positional subscale because that will allow us to stack multiple densities, and also allows us to disentangle the thickness of, say, a density or even a CDF from the orientation of the visualization if we wanted to do, say, a mapping of a distribution onto the Y-dist aesthetic instead of the X-dist aesthetic. So here, we start to use more functions of the distribution than just the quantile function, which is what we were using for constructing intervals. In the case of the traditional density chart, we're just mapping the density function of the distribution onto this thickness aesthetic. But of course, we might want to do something else, like map the density function onto fill color or opacity, or alpha, which creates a sort of traditional gradient chart. The inimitable Michaels, Carrel, and Gleicher suggested an interesting modification of a gradient chart, which only fades out outside of the 95% interval. The idea here is to both show the 95% interval, but also emphasize a little bit of its arbitrariness. We can do this using a function of the CDF of the underlying distribution. This is made straightforward in ggdist because we can map arbitrary functions of the distribution onto virtually any visual aesthetic, like alpha, fill color, thickness, and so on. In fact, we can combine these mappings with each other. So here we combine the function that creates the faded tails on the alpha aesthetic with the traditional density mapping onto the thickness aesthetic, plus the side parameter which sets on which side the thickness is drawn relative to the interval. This creates a violin plot with faded tails, which is similar to what was proposed by Helsky et al. In 2021. We could also modify this a little bit. Say we wanted to discretize the fading of the tails here. Well, one way of doing that is actually introducing back the idea of taking masses, or this gamma in this notation, and being able to map them onto other aesthetics. What ggdist does is, within any slab geometry, which is what is being used to draw the density here, at any x position in the slab, we can map various properties to that slab. This includes things like color and alpha, but ggdist also calculates for any position the mass of the smallest requested interval that contains that point. This allows us to map interval masses onto visual aesthetics of slabs and create discretized slabs like this. As a final example of something from the literature, Wilkinson coined this idea of a so-called fuzzygram used to show uncertainty in bar plots. If you imagine the uncertainty in a bar plot described as a distribution over possible bar plots, and you took samples from that distribution and overlaid them on top of each other at smaller and smaller alpha levels, as the number of samples in that chart go up and the alpha goes to 0, assuming additive blending, you would get a chart where the alpha level on each bar looks like the complementary CDF of the underlying distribution. And that's exactly what this mapping describes. You could even do things like add additional groups. So here we have a 2-bar chart with 2 groups where the uncertainty in each bar is described by how it fades out. How does ggdist actually do this? Well, here's an example of a density plot with that sort of Helsky style integrated intervals. Let's walk through how this chart is generated. So this layer consists of 2 things, a stat and a geom. The stat applies a number of statistical transformations before the geom attempts to construct the chart. So in this example, first we might specify something like a set of distributions mapped onto the ggdist aesthetic and a group mapped onto the y aesthetic. And in this data table we have 2 groups, A and B, and they each are described by a t distribution with parameters nu, mu, and sigma. Stat slab will take those mappings and generate an x grid at which to evaluate the density function, the CDF, and the masses of the smallest requested interval containing each x position, conditional on all of these distributions. Once that's done, the layer will apply some after stat mappings, and these are mappings that cannot be calculated until the stat has applied its statistical transformation. In this case, mapping the density onto the thickness and the interval mass onto the fill color of the slab. This gets passed on to the geometry, which will construct multiple polygons for each slab, one for each block of consecutive x values with the same appearance. That's how we end up with this chart with intervals drawn inside of the density plots. All of the examples I've talked through so far use the slab interval geometry in ggdist. ggdist has 2 other primary geometries, the dots interval geometry and the line ribbon. Each of these are designed to create slightly different types of uncertainty visualizations, but all of them use the same underlying distributional approach. With that approach, we can do things like quantile dot plots. We can create dot plots where the dots themselves have mappings that change their appearance, e.g. by using emojis or anthropomorphic fonts. We can combine geometries together. Here, a line ribbon combined with dot plots. We can create multiple line ribbon uncertainty charts. We can even increase the number of ribbons to a very large value so that we can create a gradient chart showing an uncertainty band. We can combine dot plots with density plots and intervals to create so-called rain cloud plots. And we can even do things like highlight important regions in a chart to show, say, the probability mass of values close to 0. If you're curious about more, please read the paper or look at the documentation for ggdist or even download it from CRAN in R. Thank you.